Hey guys, this is your lesson video for 10.6, which is about dependent events and conditional probability. If you recall, the last section, 10.5, was about independent events. So this is kind of the other side of that. So 10.5 and 10.6 kind of go together. One of them is independent, one of them is dependent. And so we're going to do a little bit of compare and contrast between the two, because I think that's important to kind of keep them straight. So our strategy here, we're going to do a couple things. We're going to talk about independent events first, again, just to kind of review some scenarios. We're going to look at some definitions and key concepts from the book, and we're going to do a couple example problems from the book. I'm going to make up a few example problems as well to help you kind of supplement that, and then we're going to do some homework problems. So I'll give you some timestamps so you can kind of navigate through the video. But let's get going here, and let's just start out with independent events. Okay. Now we define this kind of already in section 10.5, but it's a good thing to kind of refresh what independent is, because we're going to be talking about dependent, which is like the opposite. So independent events is when two events are independent if the outcome of one event does not affect the outcome of the other. So some examples of that we've seen is like if you're choosing or picking objects from two different groups. Some of the examples that we saw from 10.5 was like, okay, I want to choose a person from this class, and I also want to choose a person from this class. What's the probability that I choose both? So those are independent because you're choosing from two completely different groups, and whoever you choose from the first group doesn't affect whoever you choose from the second group. Another example is if you're choosing or picking objects from the same group, but you replace the object that you picked before you pick again. So if you're doing two selections from a bag of marbles, for example, and you pick the first marble, but then you put it back, and you pick the second marble, those events are independent because replacing the marble means that whatever you picked on the first round doesn't affect what you pick on the second one. Okay, so those are independent events as well. So this idea of replacing the object that you picked, or if the groups are completely separate, then you have independent events. Okay, and an important idea about independent events is that if event A and event B are independent, then this is how you find the probability of both happening. And we talked about in the last video that this comes basically from the fundamental counting principle. You just you use it twice, once to figure out all the ways that A and B can happen, and then you figure out all the ways that all the possible outcomes from the events, and then you divide them, and that's kind of how you get the probability. So that's all from 10.5. Okay, a new idea here is conditional probability. Now the definition for conditional probability and dependent events are kind of similar. They kind of overlap. When you have dependent events, you get conditional probability. The difference is conditional probability talks about one event that depends on another, and dependent events is like two events. So conditional probability is talking about one event, assuming something else already happened, and dependent events is just talking about whenever you have two events that are dependent. So they're very, very similar definitions. Let's take a look. We're actually going to define dependent in a second, but we're going to start with this. Okay, conditional probability. It's the probability, the probability of an event is conditional when the outcome of the event depends on the outcome of another event. Okay, so a single probability is conditional if it depends on something that already happened. Okay, so an example of that is like if you you choose a marble and you don't replace it, and then you're going to choose a second marble from the same bag, right? The second probability would depend on the first one. Okay, so an important thing to keep in mind is these events kind of come in sequence, and the outcome of the first event, what it does is it changes the sample space for the second one. If you take out a marble or you take out a card or something like that, then all of a sudden the sample space is different the second time around. Also, it can potentially change the number of ways you can get the second event to occur. It kind of depends on what you picked the first time around. For example, if you have 3 red marbles and 9 green marbles, right? As soon as you pick a marble, the sample space changes from 12 to 11, so that's obvious. But if you want to find the probability of picking a red followed by the probability of picking another red, when you pick that first red marble, not only will the sample space change to 11, but the number of red marbles that you can pick is now less as well. So when we're talking about probability, there's two numbers. There's the number of items in the sample space, the number of outcomes in the sample space. There's also the number of ways that the event you want can occur. And conditional, if one event is dependent on the other, the first event can affect both of these. It will definitely affect the sample space. It could also potentially affect the ways of getting the next event to happen. And we'll do some examples in just a second. Okay, this is some notation right here. Okay, so when you have a conditional probability, it looks like this. Okay, so this is the conditional probability of an event B given that A happened, or assuming that A happened. So this is the probability of B assuming A, or the probability of B given A, or the probability of B assuming that this thing already happened. Okay, so that's just some notation that you need to know. This is how you represent a conditional probability. Okay, so let's look at a couple examples of conditional probability, and then we'll kind of tie that into dependent events and put those two ideas together because they're very, very similar. Okay, so for this, we're just going to look at an example from the book. Example 1. This is a pretty good one. Okay, so let's talk about this scenario here. Okay, the band from Vilsdale High School has 50 members. Excuse me. Oh, sorry, let me get another piece of paper. The band at Vilsdale High School has 50 members, and the student council has 20 members. 5 students are in 5 student council members are also in band. Suppose that a student is randomly selected from these two groups. Okay, so notice that in the band circle, there's 50 total, right? 45 in band. But you have to add the 5 that are in band and student council. So the total for the band circle is 45 plus 5, which is the 50 they're talking about. Okay, in student council, they have 20 members, but we also know that 20 of those student council members are also in band. So when you look at this guy, you notice that 5 plus 15 is the 20 that you're looking for. Okay. So we want to find the probability that a student is a member of the band if you know that he or she is on the student council. Okay. So let's kind of map this out. So we want let's say event A is they're in student council. Okay, so event B is that they're in band. Okay, and remember there's 50 students, or there's, let's see how the total here is. We got 45 plus 5 is 50 plus 15. There's 65 students total. It seems like there's 70 because you're like, well, there's 50 and 20, right? But remember that we have to subtract out the overlap because we don't want to count it twice. If we're counting, these 5 bands, or these 50 students, 5 of these are also student council members. We don't want to count this 5 twice. So if we do 50 plus 20, we doubled that middle number. We don't want that. So there's 65 students total. Okay. So if we wanted, we want to find the probability the student is a member of the band. Let's do it a couple different ways. Let's just find the probability of B. Okay. Probability that the student is in band. Okay. Well, how many students are in band? There's 50, right? How many students are there total? There's 65. So the probability that the student is in band is 50 over 65. I'm going to simplify that really quick. They're both divisible by 5. Okay, so that's 10 over 13. And then as a decimal, that's approximately 0.77-ish. Okay. But that's not what the question's asking for. Okay, the question is asking a little bit different, but we're just going to compare and contrast. The question's asking for what's the probability of B given A. Okay, in other words, what's the probability that the student is a member of the band if you already know she's on student council? Okay, so what happens is the first event already happened. In other words, the first event is we decided the student was in student council, or we picked a student that was already in student council. And so what's happening is we're changing our sample space, because now we're not thinking about how many students are total. There's 65 total. We're talking about, well, how many students are in student council? Because event A already happened. We already picked a student that was in student council, and there's only 20 of those, right? So the sample space now is different because we're looking at a subgroup. We're assuming, let me move this up a little bit. We're assuming that the person is in student council. So making that assumption, or making, the assuming that event A or the student is in student council already changes the sample space. Okay, so now we got to figure out, well, how many students are there to choose from? There's also only 5 students we can choose from. So you can see that it changed the sample space. It also changed the number of ways that event B can happen, because we can't choose any of these band students. Okay, so this is 5 out of 20. Which is, they're both divisible by 5, so 1/4, which is equal to 0.25. Okay, so this is the probability that B happened on its own. This is the probability that B happened assuming another event already happened. This is a conditional probability. This is just a regular probability. Okay, so just note how the sample space changed and the number of potential outcomes changed, or the number of outcomes that we wanted. Okay, so that is that's a conditional probability. So conditional probability is just one. That's still the probability of a single event. It's just the probability of a single event, assuming that another event already happened. Okay. All right. Let's look at another example. This one is one that I made up. Okay. So let's take a look at this. A random card is pulled from a deck of 52 playing cards. The card was a diamond. Find the probability that the card is the ace of diamonds. Okay, so again, we're going to do a little compare and contrast. So let's say event A is pulling a diamond. So you're going to pull a single card out of the deck, and you want it to be a diamond. Okay, the probability of B is pulling out an ace of diamonds. Okay, so if we wanted the probability of B, which is not a conditional probability, that would just be the number of ways I can pull the ace of diamonds, which is 1, out of the number of ways that I can pull a card from a deck of 52, which is 52, right? That's just a regular probability. A conditional probability basically assumes that something already happened, okay? So this conditional probability is like, okay, you pulled this card. Now let's say that card was a diamond. So you're like limiting the number of options. So this is the probability that you're pulling the ace of diamonds, given that the card you pulled was already a diamond, or you're already assuming it's a diamond. Okay. So what's happening is you're trying to figure out how the sample space is changing. Okay. Well, there are 13 diamond cards in a deck because there's 13 of each suit. 13 diamonds, 13 hearts, 13 clubs, 13 spades. Okay, so there's 13 diamonds total in a deck of cards. And if you didn't know that, that's okay. If you're not familiar as much with playing cards, it'll still work. But just, take my word for it. There's 13 diamonds in a deck. Now, if you pulled a diamond, you know that's a diamond, then how many ways are there to pull an ace of diamonds? Or how many ways are there for you to get an ace of diamonds? Well, there's still only one ace of diamonds in the deck. So there's one way to get that ace of diamonds, but now your number of outcomes has changed. Okay, so these are two different things. This is the conditional probability. This is what the question is asking for. This just compares it to an older idea. So this is what we're after. Okay, so that's what a conditional probability is. It changes the sample space. Now notice that the number of ways that event B could occur didn't change in this case. It doesn't always. In the previous example, it did. The number of ways that you can pick a band member changed. Sometimes it doesn't, but it will definitely change the sample space. Okay. Let's talk about dependent events. So dependent events and conditional probability are very, very similar. The difference is conditional probability is talking about just the second event, and dependent events is talking about two events together, like the first event and the second event. Okay, so in this case, we think we have a conditional probability, but we would also say that these are dependent events. So this is a single conditional probability, but we also know these two events are dependent on each other. So conditional probability refers to one outcome given another. Dependent events refers to the relationship between two events happening. But they're similar ideas. So dependent events. Two events are dependent if the outcome of one affects the outcome of the other. Okay, well if that's the case, then one of them is going to be a conditional probability, right? So similar ideas. Okay, we get dependent events in a couple scenarios, or there's a couple common scenarios that we've seen. So choosing or picking two objects without replacement, right? Because again, if you take a card and then don't put it back, or you take a marble out of a bag and you don't put it back, you're changing the sample space. You're changing the number of outcomes you can possibly choose. Also, if you're choosing or picking an object from a subgroup or category, okay, we saw that in the example of that Venn diagram that we were looking at, because we're like, the first event is like narrowing it to a subcategory, right? So you're like, given that they're in student council. So that subgroup or that subcategory, narrowing it down to a smaller group of people to choose from, that's kind of like your first event happening, and then the second event is picking from that subgroup. So those would be dependent events as well. Okay, one thing to keep in mind and to compare and contrast is that we have a different formula for the probability of two events happening with the and if the events are dependent. Okay, so this is very similar to the formula that we had originally for A and B, but the difference is that this piece is different. Okay, so I'm trying to find my other paper that I was using. Hang on. Okay, I'll just write it again. So there's two formulas here. So this is for dependent events. Okay, for independent events, which I had on the first page, the probability of A and B is equal to the probability of A times the probability of B, because B doesn't depend on A happening. So they're very, very similar formulas. Okay, this is the one we used in 10.5, assuming the events are independent. This is the formula that we use if they are dependent. Okay, so the difference is this is the probability of B, this is the probability of B assuming that A happened, because B is dependent on A. Okay, let's do an example. We're going to look at both cases. Okay, so this is, again, another one that I made up, but it'll help us compare and contrast between independent scenario and a dependent scenario. Okay, so find the probability of choosing the ace of diamonds followed by the king of diamonds in two draws from a standard deck of 52 playing cards with and without replacement. Okay, so let's start with without replacement. So I have two draws. Okay, the first draw doesn't depend on the second draw. Sorry, because we're sorry, let me go back. I got this backwards. We want to do with replacement first. And then on this side we'll do without replacement. Okay, so the first one we're gonna pull a card and then we're gonna put it back in the deck. So in this case, we're talking about independent events. Okay, independent events means we're going to be using this formula. So the probability of choosing a ace of diamonds, I'm just going to use symbols here, and a king of diamonds in two draws is going to be equal to the probability of choosing an ace of diamonds times the probability of choosing a king of diamonds, because they are independent events. Okay, so there's 52 cards in the deck. There's only one ace of diamonds, so this is a 1 out of 52 chance of pulling that ace of diamonds. Then you put the card back in the deck and you reset So now you still have the same 52 cards to choose from. You could still choose that ace of diamonds potentially, but we want the king of diamonds now. There's only one king of diamonds, and there's 52 ways to do that. Okay, so when you multiply these two probabilities, we'll see what we get. It's 1 over 52 times, whoops. Okay, so that's 1 over 2,704. And just as a decimal so we can compare, that's 0.00037. So pretty unlikely for that to happen. Now this is going to be unlikely too, but let's just look at the difference. Okay, so without replacement now, we're pulling the card, we're not putting it back, and all of a sudden the second event is dependent on the first event, because if I choose the ace of diamonds on the first go-around, then I have less cards to choose from, and so the probability of choosing the king of diamonds is going to be different. So we're going to do the probability of ace of diamonds and king of diamonds in two draws, basically, is going to be equal to 1 over 52. There's the first time around, I want the ace of diamonds. There's only one of them. There's 52 ways to choose it. The second time around, I want the king of diamonds, and assuming that I chose, actually, let me write this out. Let's do, so this is the probability of the ace of diamonds times the probability of the ace of diamonds, assuming that I already, this is king of diamonds. I want the probability that I'm choosing the king of diamonds, assuming that I already chose the ace of diamonds. Okay, so the probability of choosing the ace of diamonds, again, is 1 over 52. There's one ace of diamonds in a deck of 52 cards. Now, assuming that I chose the ace of diamonds already and I didn't put it back, there's now only 51 cards to choose from, because I chose a card already. So this, choosing the king of diamonds, is dependent on what I chose the first time around. There's still only one way to choose that, so the sample space has changed. And that's going to give us 1 over 2,652, which is still pretty small, but it's more like 0.00038. So it changes the probability a little bit. Okay, so this is dependent events. Dependent events includes this kind of conditional probability. The second event is dependent on the first one. So those go together. When you have dependent events, you're going to get conditional probabilities. Okay, this is what we did in 10.5. This is what we did in 10.6. Okay. All right. Let's do some homework problems now. Okay. This is your homework assignment. Once again, I'm just going to try to do a few from each one, each little problem set. But I'll also kind of introduce, if I'm not going to do one, I'll introduce the idea and kind of get you started. So it starts with 4, 5, and 6. Let's take a look at that. Okay. So number 4. The band at Washington High School has 25 members and the pep club has 18 members. 5 students are in both groups. Find the probability that a student randomly selected from the 2 groups is a member of the band if you know that he or she is a member of the pep club. Okay, well that's very, very similar to example 1 that we did, right? So you can refer back to example 1 in the book. We did it together. I would start probably by making a Venn diagram and kind of mapping it out. So I'll help you with that real quick. So we got band, we got pep, and the band has 25 members, but there's 5 in both, so 5 here, 25 total, so 25 minus 5 is going to be 20 again. Kind of similar to the other one. I think it was 40 and 5. And then this one, there's 18 students in pep club, but 5 are in both, so 18 minus 5 would be 13. Okay. So the total amount of students is going to be 20 plus 5 plus 13. So it's like 38. Okay. Again, just to kind of be clear, if we added 25 to 18, 25 plus 18, that's like adding 20 plus 5 to 5 plus 13. There's your 25, there's your 18. I don't want to do that. That's going to give me too many people. So if you're just like, oh, there's 25 plus 18 students total. There's 43 students total. What you did is you just counted the middle part twice. You counted them here and here, which is why if we want, if we want A or B, we have to do A plus B minus A and B. So we have to do 25 plus 18 minus the extra 5, and that will give us 38. So regardless of how you kind of figure it, there's going to be 38 students total, but that just kind of want to refresh on kind of an OR scenario where you add probabilities, okay? Or add, in this case it's events, or a number of students, but the idea is the same. Okay, so that's how you're going to set this up. Now, the key here is that you're assuming that they're already in PEP Club. So the first event, really, we want to find the probability of B assuming A. The first event is that you're narrowing it down to the fact that they're in PEP Club, okay, which changes your sample space. Your sample space isn't going to be 38. That's the total number of students. Your sample space is going to be the total number of students in PEP Club. Right, so that first event is, okay, let's narrow it down to PEP Club, and then of those students, what's the probability that you're pulling a student that's in band from those students? Okay, I'll let you finish that one up, but that's kind of the setup there. Okay, 5 and 6 go together, so we have a bag containing 12 blue discs and 5 green discs, which is 17 total, so the sample space is 17 for the first pick. For each case below, finding this probability of selecting a green on the first and then a green on the second. Okay, so in the first scenario, the disk is replaced, right? Which means that this is an independent scenario. In the second one, the disk is not replaced, which means the second draw is dependent on the first draw, which means the second draw is going to have a different sample space, and there's also going to be a different number of ways to choose green disks, because you're going to have one less green disk to choose from if you've already chosen one. Okay, so this is kind of the compare and contrast between independent and dependent. So if you need help with those, I would go back and look at this example here. This is example 2 from your book. And I actually did this example in the 10.5 video, just because we were talking about independent, and so I wanted to compare and contrast independent, dependent. So we actually already did this example, but you can look through that one. You can also go back and look at the examples that I did in this video with the cards. I talked about choosing a card with replacement and without replacement. And so you can kind of look at those. But those are very, very similar to what we've done. All right, let's look at some problem sets here. So I gave you guys 13 through 16, which is these 4. So I'm going to do 13 with you, and then you can do the other 3. So we got a bag that contains 8 red, 8 yellow, and 5 blue. Okay, so altogether that looks like it's going to be 22, I think. Yep, 22 total. And then we want to do 2 draws, and we want to find the probability of each event. Now remember, this is without replacement, so this we're talking about dependent events, which means the second probability is going to be conditional probability. Okay, so 19 is we want to choose red followed by yellow. Okay, so this is probably more detailed than you need, but just to kind of reinforce the key concepts here. So event A is pulling a red. Okay, event B is pulling a yellow. Okay, so the probability of A and B would be the probability, it would be this. It would be red first and yellow second. So that's how we would write that. Probability of red and then yellow, and this in this order. Okay, so the probability of those both happening is the probability of pulling the red multiplied by the probability of pulling the yellow, assuming I already pulled a red one out. because remember this second event, event B, is going to be dependent on event A. Whatever I pull in event A is going to change my sample space. Okay, so this is kind of where we're after. We're talking about dependent events, which means this second probability is going to be a conditional probability. Okay, so let's take a look. If I have 22 disks total and 8 of them are red, there are 8 out of 22 ways to pull a red disk. Okay, so that's the probability of A. Now the probability of B assuming A, notice that if I pull a red disk, then I have one less disk to choose from. My sample space is now 21 disks. This is one less. Okay, so I still have those all 9 yellows to choose from. I just, I have less total. Okay, so the sample space has changed by event A. Event A affected event B. So I just need to multiply these together, no big deal. You can use a calculator to do that. There's ways to, you could simplify a little bit first if you wanted to, because 2 goes into both of these, for example, and 3 goes into both of these. So you could say this is a 4 over 11, and this is 3 over 7. That might make your life a little easier. And then when you multiply, you get 12 over 77. Okay, so either way, you're going to kind of get the same thing, and I don't know, you can write it as a decimal if you want, but the answer in the back of the book is probably going to be a fraction. So I'm just double checking here. Okay, and then we'll change it to a decimal. So this is our exact answer, but if we wanted to approximate it, we would say that it's about 0.156, or it's about a 15.6% chance of that happening. Okay, so the rest of these 14, 15, and 16 are going to be similar. You just need to, kind of write it out and change the sample space on the second one. So very, very similar, but you're multiplying again. Remember, when you have an and, you're going to multiply probabilities. When you have an or, you're going to add probabilities, but there's 2 cases for each. Okay, let's look at the next problem set here. Okay, so 2 number cubes are rolled. The first cube is a 5. Find the probability of each event below for the 2 cubes. So in this case, we're not finding the probability of, we're kind of finding the probability of 2 events, but the first one is already given to us. We already have the first one. The first one's, already done. So we're kind of finding a conditional probability in this case. Okay, so if we roll a 5 on the first one, how can we get a 9? How many different ways are there to sum to 9? Well, if the first one's a 5, there's only one option for the second roll, and it's that we roll a 4, because that's the only way that's going to happen. So we'll kind of map this out or write this out so we can kind of make sense of it. So what we want, so the event A is rolling a 5. Event B is sum of 9. Okay. And we want to find the probability of B assuming A. Okay. Now, if we want to just the probability of B, which we don't, so if we want to just the probability of B, we would say, well, how many different ways are there to roll a 9 with 2 different rolls? Well, there's 5 first and then 4 second. There's 4 first and then 5 second. There's a 3 and then a 6. There's a 6 and then a 3. Let's see, are there any other ones? 2's not going to work. I think those are the options there. I think there's 4 of them. So there's 4 ways for that to happen when you're rolling, 2 dice out of the 36 total options that you could potentially have based on that table that we made in the last couple lessons ago. So you would normally say, well, there's 4 out of 36 ways for this to happen, right? Which is 1 out of 9. Okay, but that's not what we're after. We're assuming something already. We're assuming that the first one is already a 5. Okay, so the probability of getting a sum of 9, assuming that we already rolled a 5, is a conditional probability And the ideas are, okay, we're only rolling one die. We've already rolled the first one. How many different outcomes are there from rolling the second die, or the second number cube? There's 6. There's the 1, 2, 3, 4, 5, or 6. There's only those 6 outcomes because the first event already happened. Okay, so the sample space hasn't really changed here for the second event, but the outcomes will kind of change. I guess the sample space did kind of change because it was kind of 36 to begin with. But how many ways are there to get a sum of 9 if the first one's already a 5? There's only one. There's only one number that will add there. So this is just 1 over 6. Notice that these are different. Okay, so the probability of B, assuming that like there's just 2 rolls and I want to sum to a 9, there's one. That's the probability is 1 out of 9 because there's 4 ways to do that and there's 36 total options. The probability of B assuming A is saying, okay, like this already happened. So now all of a sudden our sample space is different. It's at a 6 instead of at a 36. And also the number of ways that can happen is different because there's only one way for that to happen. So this is the one we're after. This is just kind of to compare it to something we talked about before. Okay, so you're going to do the same kind of idea. So for 18, you got the probability of 2 odd numbers. Well, the first one is already odd. So the second one has to be odd. So how many ways are there to roll an odd on a roll? There's really only 3 ways to do that. So anyway, I'll let you finish that one, but that's kind of the idea. Okay, we got 20 through 23, so you're going to do these 4. I'm going to do 20 and 21 with you. That will kind of set you up for 22 and 23. Okay, we're going to do them kind of quickly because I know this video is getting to be kind of long. All right, so for one roll of a number cube, let A be the event even and B be the event 2. Find each probability. Okay, so number 20, the probability of A is the probability of even, right? So how many ways are there to get an even on a dice roll? There's 3 ways for that to happen, 2, 4, and 6. How many options total are there? There's 6, so that's just 1/2, right? That's not really anything new. That's not a big revelation. Okay, B is the probability of A and B. So when you're rolling a die, you're not taking anything away. So these are like independent, basically. You're rolling one and then you're rolling the other. So these are independent events. We don't have to really worry too much about overlap. One outcome is not going to affect the other one unless you kind of force it to, which we will in a second. So the probability of A and B is the probability of A times the probability of B, which is the probability of even times the probability of 2. So the probability of even, again, is 3 over 6, or 1/2. The probability of 2 is 1/6. So if we multiply those together, the probability of A and B is 1 over 12. That doesn't seem right. Hang on a sec. Probability of A and B should be 1 over 6, I think. Even and 2. Shoot, I'm gonna have to stop the video there and come back and fix it because I just spaced out. Hold on a sec.